Hello, everyone. Welcome to this edition of zkStudyClub. Today, we're very excited to welcome Benedikt Bünz, who's been a guest before, and also Binyi Chen on their joint work that they also did with Dan Bonnet and Jinfei Zheng of Espresso Systems. And Dan is, of course, with Stanford University. And the title of the paper is HyperPlonk, and it's talking about their work optimizing the Plonk proof system. So Binyi, with that, please take it away.
Thank you, Alex. So yeah, today I'll be presenting HyperPlonk, which is an adaptation of the famous Plonk proof system that's adapted to the boolean hypercube using multilinear polynomial commitments. So this scheme has linear time prover and also has very nice support to the high degree custom gates. So also it's high parallelizable and hardware friendly because it removes the use of FFTs. So before diving into the details and stating our results, let me really quickly go through the notions of snarks and its building blocks. So our main goal is to building a preprocessing snarks, which is basically a scheme that enables the prover to convince the verifier that he knows a valid witness to certain public circuits. And the goal is to have small communication and a small verification cost. So it consists of three algorithms. In the setup phase, this preprocessor will take as input the circuit and output some public parameters. And then the prover, given the parameters and an online witness to the circuits, will generate the proof and send it to verifier. And the verifier, after receiving the proof, will check it and output accept and reject. And we hope it to be complete, meaning that all these provers should always succeed. And we hope it to be knowledge sound, meaning that if verifier accepts this proof, then it must be the case that prover exactly knows the underlying witness, okay? And also for it to be snarks, you also need some succinct property, meaning that the proof size and the time for verification are all very, very small, meaning the sublinear to the circuit size or even logarithmic to the circuit size. So that's the snarks. And I want to say that many recent snarks were built using the following framework. So what they do is they start by designing an interactive protocol in the ideal world called polynomial IOP, and then they compile. And there are some many examples like Plonk or Sonic or Marlin or Liberal and many more. They are all falling this category of poly IOP protocols. And then after that, they will try to compile this ideal protocol into a non-interactive succinct arguments by using a control primitive called the polynomial commitment schemes. An example includes the famous KZG commitments and also in the product arguments based one, including Boolean proofs, and also FRI-based one, and also the dark, which is built from group of unknown order, and there are many more. So this framework is like the very good property of this framework is that highly flexible and modular, meaning that you can just combine any one of the poly IOP with any one of the PCS, and you obtain a new snark for general circuits that has different kind of features. And I will quickly remind you what is poly IOP is. So essentially, it's just an interactive protocol. Well, in each round, the prover will just send some polynomials to the verifier, and the verifier will reply with some public random challenges. And then finally, the verifier can also query some evaluations on these polynomials and check certain relations holds between these evaluations. And we'll also note that this is very general. You don't need, the polynomial doesn't have to be always univariate. You can also extend to multivariate setting where the polynomial has multiple variables. Each variable has different degrees. So of course, this kind of ideal protocol is definitely not a snark, right? First, it's interactive, and also the polynomial is so huge and so too large to be sent, and it's too costly for a verifier to just evaluate the polynomial himself. So we need some crypto primitives to compress this polynomial and enable some efficient evaluation checkings. And this is so-called polynomial commitments. So given a polynomial with some bounded degree, the prover can commit it to some bit strings, which length is independent of the degree, which is very short, and required to be binding, meaning that the prover cannot open this commitment with different types of polynomials with bounded degree. And another feature of PCS is that it allows the prover to convince the verifier that certain evaluation holds true with respect to these committed polynomials. So the prover will generate a succinct evaluation proof that is knowledge sound, meaning the same property, like meaning the verify, if verifier accepts, that means that prover must know the underlying polynomials, meaning that there's some way to extract these polynomials from this prover. Okay, so yeah, that's the background. As I think most of the audience already familiar with backgrounds. So now we are ready to state our main results. So the key result we have is we built a new multivariate poly-IOP that adapts this Plonk univariate IOP into the Boolean hypercube using multilinear commitment schemes to obtain the final snarks. So the good feature of this scheme is that first, it's fully linear and highly parallelizable because we fully remove the use of FFTs, which has quasi-linear complexity and can be hard to parallelize when the instance size is large because it has really complex memory access patterns. So this makes it favorable for applications like zk rollup or zk EVM that has like gigantic, like very, very large circuit size. So the second thing, and I think even more importantly, is that it gives a really good support to the high degree custom gates. So what is custom gate? Custom gate is one of the Plonk's like really nice features that enables developers to design their own gate types for arithmetic circuits so that they can minimize the circuit size for their own applications. Just take an example. So with the help of high degree gates, you can express elliptical curve addition, for example, with only 2 constraints, where if you use R1CS, it can take many more constraints. So however, this kind of custom gate is not very, like, there are some limits in the case of Plonk, because in the Plonk, the number of group exponentiations being conducted is proportional to both the number of gates and also the degree of the custom gates. So it's like there's a multiplicative relation in it, so which limits the feasibility of using a very high degree gates in the design. And in contrast, our poly-IOP, like after plugging it with a PCS, like only has additive complexity with respect to the number of gates and the degree gates, the degree of the gates. So it allows us to use much higher degree gates without like affecting the performance of the proof system. So after plugging this PIOP with a PCS, like a variant of KZG in the multilinear setting, we also have very good concrete proof size for the resulting snarks. It's basically like 6 kilobytes to 7 kilobytes for most of the like possible application of circuit size. And along the way, we'll also build some efficient batch evaluation methods and made these things to be zero knowledge if you want in the multilinear setting, which is also non-trivial and can be of independent interest. I think is there any questions in the chat? Oh, okay, no.
Nope.
Okay, thank you. Okay, so beyond that, we also extend this HyperPlonk to also support lookup gates, which is a very important custom gates. Basically, we extended the famous lookup methods to the Boolean hypercube, and in the multilinear setting, obtain a first linear time lookup poly-IOP. And finally, we also construct some new multilinear commitment schemes that can be plugged into HyperPlonk PIOP to obtain some new snarks with different nice features. And one highlight is that we improved the recent Orion PCS, which has really fast prover. Basically, the prover complexity is like it's only linear number of field operations plus some very fast hash operations. And our contribution is that we preserve its linear time prover, but improve its proof size from several megabytes to several kilobytes. So it's almost like 1,000 factor of savings for the proof size. And beyond that, we also build some very simple FRI-based multilinear commitment schemes, which is, I think, is simpler than Virgo, but like with using some other tech ideas. And yeah, so that's the general contribution we have made, and the rest of talk will be organized as follows. So I first explain how do we adapt the Plonk to the multivariate setting and build the multivariate polynomial IOP, and then I'll explain how to handle the high degree gates and do the batching for it. And next, I'll describe techniques for supporting lookup, and finally, I'll give some very grain of salt evaluations and benchmarks. Okay. So let's get started for the HyperPlonk part. So before describing the HyperPlonk poly-IOP, I'll quickly review the workflow of Plonk. So given an arithmetic circuit, the first step in Plonk is that I compile the circuit into a trace, which is basically a matrix, and then encode this matrix using some univariate polynomials, interpolate them basically. And then I need to prove that this trace or this polynomials exactly encodes a valid circuit computation, meaning that circuit will output 0, like given these gate values. And this is done by 2 checks. First is a so-called gate identity check, meaning that every gate value are consistent, meaning the inputs and output are correct with respect to this addition or multiplication gates. And second, I will need to do a wiring identity check, meaning that different gate values should be consistent, say identical, if they're connected by the same circuit wires. So I'll dig deeper on each step in the following slides. So let's first see how do we do the encoding. So given a fan-into arithmetic circuit, for example, with n gates, what we do is that we translate this circuit into a matrix with n rows and 3 columns. So where each row now maps to a gate, right? And each column maps to the left and right inputs of the gate as well as the output of the gate. So for example, there's a gate 0 here, which is the addition gate with input 5, 6, and 11. So that the first column is 5. So the first row is 5, 6, and 11. So this is the way we transform a arithmetic circuit to a matrix, which is so-called trace. And then the Plonk uses the univariate polynomials to interpolate these columns of the matrix so that it can conveniently conduct some polynomial equation checks later. So you can see here, for the first column, I use a polynomial L to interpolate these column values into a multiplicative group in this univariate polynomials, where omega is the root of unity. And similar thing holds for R, which is another polynomial, and O. And now the key thing is like there's some caveat of this kind of method is because that in order to interpolate these values, and because in the underlying protocol, sometimes you need to use the coefficient form of the polynomials. So the encoding here, you need to do some fast Fourier transform here, which we'll call FFT or NCT. And the fast FFT has complexity n log n, and also it requires the use of some FFT-friendly fields, meaning that it has a really large multiplicative group inside it. So this makes something bad, not very good when the instance size is super huge. And oh yeah, as I want to say that it's less parallelizable because it involves very complex memory access patterns. But I would say that this is not a big issue. Plonk is really useful and widely used in the world because because FFT only involves field operations. It's much more efficient than the group exponentiations. However, because you see that FFT is quasi-linear, so when n keeps growing, this becomes a problem. For example, when n comes to the 2 to the 20, it becomes significant part of the cost. When it comes to the 2 to the 30, it's even more significant. It might become bottleneck. And also, as we said, that it also hinders the hardware optimization because it's very hard to do parallelizations. So given this, we'll address this issue by interpolating this matrix using multilinear polynomials and interpolating these values using Boolean hypercube instead of a multiplicative group generated by roots of unity. So you can see here, I interpolate 5 into 0, 0, 5 into 0, 1, and 1, 0, and 1, 1. So this is a Boolean hypercube with dimension 2. And similar things holds true for R and O. And this polynomial can be interpreted as some polynomials with 2 variables. So the advantage of using this kind of encoding is that the underlying protocol we used or use the polynomial in its evaluation form. There's no need to do anything about coefficient and evaluation form transform. So you basically need to do nothing when you do encoding. And here I want to emphasize that now, in this multilinear polynomial, there are log n variables, and for each variable, the degree is 1. So it's basically linear in each variable. And we also mentioned, similar to the univariate setting, there are also many polynomial commitments works for multilinear polynomials, including KZG-based, FRI-based, fully proof, and Dory. There are many more. and most of them are also relatively efficient, meaning that proof size and verification are all O log n with very good constants. So I want to say that this kind of idea is not brandly new. Actually, like Spartan and Cox, they also use some similar ideas to interpolate witness into multilinear polynomials. But the difference here is that they work for another type of constraint system called R1CS rather than the Plonk constraint system. Okay. So after talking about encoding, let's see how we make sure that this trace is correct and is encodes the valid computation. So the first thing is that we need to ensure that this trace encodes is consistent with each gate. And this is done by checking a unified equations holds true for every point in the interpolate set H. So basically we need a way to unify. So you recall we have addition gates and multiplication gates. So we need a way to unify both gates into a single formula. And Plonk addressed it by introducing some preprocessed polynomial called the selector polynomials that encodes different gate types. So basically, if there's, for the ith gate, if there's an addition gate, we set it to be 1. If it's multiplication gate, we set it to 0. And now we only need to check that for each point in this interpolate set, the following formula is evaluated to 0. And let's see why it encodes both addition gates and the multiplication gates. So when there's an addition gate, we set S to be 1. So you can see the left-hand side is activated and the right-hand side is inactivated, turned off. So we obtain a constraint about addition gates. And similarly, if S equals 0, we obtain a multiplication gate. Like the right-hand side is activated, the left-hand side is turned off, and we constrain a multiplication gate. So that's the idea of Plonk, to unify everything in a single formula. So that now the problem is reduced to basically a zero-check relation, where one wants to check that a formula holds true, or say a formula evaluates to 0 for every point in the set H. And Plonk builds a protocol for this zero-check relation by showing that this polynomial is divided by a zero polynomial that values on this set H, so that f evaluates to 0 on every well in H. Or equivalently, by showing that f is the product of the zero polynomial and the so-called quotient polynomial here. Okay, so that's the idea of Plonk. However, now we've used multilinear polynomials, and everything is now embedded in Boolean hypercube. And there is no such easy quotient check now in the multilinear setting rather than in the univariate setting. So instead, we still can use a standard trick to transform this zero check actually into a very classic sum check protocol and solve these issues. Essentially, if f is evaluated 0 everywhere in this Boolean hypercube, then we can interpolate these coefficients and say, oh yes, the corresponding interpolated polynomial over this variable z is actually identically 0. And then we can use the very famous Schwarz-Zippel lemma to say, okay, then that means for a random vector z, the corresponding equation should be 0. And this is exactly a sum check, which check that the evaluation of some polynomials over the Boolean hypercube is exactly some certain values like 0. And even better, using this kind of idea, using this sum check protocol, can further improve the prover time from quasi-linear to linear, because we no longer use FFTs or even the FFT-friendly fields. Okay, so that's about gate checking. And the other thing is that we also need to ensure that different gate values are consistent if they're connected by the same whiles. For example, here you see that 7 is the output of gate 1, and which is also the right input of gate 2. That means that the corresponding value should be consistent, right? And similar holds true for other kinds of color slots. So if they are connected by same whiles, they should have the same value. So Plonk solved this issue by proving that this witness values LRO should be a prefix permutation of itself, where this permutation hard codes the wiring information of the circuit. And Plonk gives a very nice idea to do a permutation arguments. But what we get is we give explain it in a more modular way. essentially we build a more modular framework explaining these ideas, explaining the dependency of these protocols for different types of relations. Okay, and more importantly, we extend these relations, this kind of reductions into the multivariate setting. And the key difference here is that at the bottom, we replace the Gaussian check with the classic sum check protocol. And this is also the core reason why we can like get rid of FT and obtain some scheme that has linear time prover. Okay, so that's about how basically HyperPlonk works. And I also want to highlight there's a key advantage to moving to the multilinear setting is that it enables much better high degree custom gate support. So we recall that in this simplified Plonk constraint formula, or like I would say called vanilla Plonk constraint formula, there's a degree 3 formula because like there's L times R times S. But in practice, we can definitely use other types of gates if you want. For example, you can replace the multiplication gates with some much higher degree gates, like some toy example is L to the 5 plus R. And more generally, we can definitely embed more custom gate types in this formula using different selectors. And a key benefits or key advantages of doing this is that it helps you to reduce the size of the circuit or witness for certain applications. And that means you don't need to prove a really large circuit, you can prove a much smaller circuit, which makes sense to help you to have faster prover, right? And there's some examples. For example, with the help of high degree gates, you can express a ECC addition with like much fewer constraints, and same thing holds for true for some algebraic hash functions like rescue or something else. However, the power of this custom high degree gate in Plonk is kind of limited because recall that it involves some protocol called quotient check. What the quotient polynomials its degree is actually multiplicative to both the number of gates and the degree of the custom gates. So it has degree dn. And after plugging into a PCS, we also need to commit to this quotient polynomial. That means it also increases the number of group exponentiations of this underlying protocol. And we know that the PCS part is actually the very heavy part of the snarks, and this makes the proving performance worse if we use a really high degree gates. And also because we have a quotient check, which is checking like the product of two polynomials, we also need to do some higher degree polynomial multiplication, which implies some larger size FFTs. So in practice, the recommended degree used is usually not too large, like usually like less than 8. If you goes to even higher, then the advantage of using high degree gate is trade-off or canceled by the deterioration of the proving performance per gate. But in contrast, the HyperPlonk has the advantage that these high degree gates only mostly affect the underlying information theoretical protocols, namely the sum check protocol. And we know that sum check consists mainly just of field operations rather than group operations. And also sum check, in each round, there will be some univariate polynomials, but it's only degree D, but not degree Dn. So that means like we don't have a very, very large degree polynomial to be committed. So essentially, I want to say that this enables the use of very, very high degree custom gates. And even if you are using very high degree custom gates, the cost of the sum check over this high degree polynomial can still be comparable or even less than the proving cost of the polynomial commitment part. And the entire cost won't increase much, even if we use very high degree gates. And this is justified by our benchmarks as well. We show that the proving cost is only 20% more expensive when we switch from some gates with degree 2 or 3 to degree 32. Okay. So meanwhile, I want to very quickly say that we also have some optimizations to the classic sum check protocol tailored for the high degree polynomial setting. I won't go into many details on the exact improvements, but I do want to highlight a key property of this classic sum check protocol. So the sum check protocol is basically a very efficient protocol for you to argue, for the prover to argue that the sum of evaluations of a Martin-linear polynomial over the Boolean hypercube equals certain values. And the key property it has is that it reduces these like almost 2 to the mu evaluations of f to a single random evaluations of f. So basically verify I only need to check a single evaluation of these multilinear polynomials. And this is very good property, and it can be super useful in some other scenario, which we will see later. Okay, so I won't go too much on this. So let's summarize what we get. So now, like after having this, we know that we obtain a HyperPlonk, which is a multivariate polynomial ILP for the MP relation or arithmetic computation. And in the pre-processing phase, what the preprocessor does is that it will send some oracle called selector polynomial and permutation polynomial, where selector polynomial encodes those gate types, including like addition gates and multiplication gates and or even custom gates. And the permutation polynomial encodes like hard codes those information for the circuit whiles. Okay. And then in the online phase, the prover will send the witness or like circuit witness polynomials here LRO to the verifier. And I also want to note that in the Martin-linear setting, it's very easy, like after when you do the snark, when you do the commitments, it's very easy to combine them together and just obtain a single commitment for all of them. So basically, you only need to send one commitment in each round. And then after that, what we need to do is just to run this poly ILP for the gate check as well for wiring checks. And all those protocol, their underlying protocol, or just the sum check over some higher degree polynomials. And we also note because sum check is really batchable, has really good property about batching. So we only need to have a single sum check for both poly ILP, and this can save us some like proof size and improve the efficiency of the protocol. Okay, so after that, we know that finally the verifier we need to evaluate this big, very complicated polynomial at a single point, but actually it turns out it corresponds to like many evaluation queries to the many Martin-linear polynomials. So in the vanilla setting, in the vanilla Plonk constraint system, we already need like 14 polynomial evaluation queries for the verifier. And this is not very good because that means if you plug into a PCS, then we need to generate many PCS evaluation proofs, one per evaluation queries. And PCS evaluation proof in the Martin-linear setting is exactly one of the bottleneck of the proving time. And it's very, very expensive. So we don't want to build so many evaluation proof where we just cancel out our efficiency of the poly ILP protocol. So given this, to address this issue, we also design a new poly ILP for the batch evaluation so that we can reduce the multiple number of evaluation queries on Martin-linear polynomials into a single evaluation query on a single Martin-linear polynomial. And hence, the resulting snark only needs to provide a single PCS evaluation proof, which is much more efficient. Okay. Okay, so let's look a little deeper on how this batching works. So here, the prover's goal is to convince the verifier that K polynomial evaluations are consistent, are correct, where each query can involve different polynomials and also different evaluation points. And we hope to build some like information theoretical protocol that transform these K queries into a single query to this Martin-linear polynomial. And we also hope that this protocol is very, very efficient. Namely, the prover time should be not much larger than the time complexity of doing these K polynomial evaluations. And second, we also need this protocol to be really efficient, meaning that the communication or proof size should be logarithmic and the verification time should be also logarithmic. So it doesn't add much overhead of the underlying HyperPlonk protocols, okay? So we note that there do exist certain protocols that deal with these so-called batch evaluation problems, but they do not meet our requirements here. So first, Halo Infinite is a very good work that also do batch evaluations, but the key thing is that they only work for univariate polynomials, but not generally for multivariate polynomials. We also know that Justin Taylor's book has also proposed some solution for these batch evaluations for multilinear polynomials. However, after generalizing this approach into this setting that, well, we have multiple points and multiple polynomials, the solution only has prover time k square mu times 2 to the mu, where k is the number of evaluation, mu is the number of variables in these polynomials, which is far from optimal because the complexity of evaluating k polynomials is only with complexity k times 2 to the mu. So given this, we improve the state of the art by proposing a new batching protocol with prover time only k times 2 to the mu, which is almost optimal because you anyway need to take this much time to evaluate the k polynomials. Also, this is basically a k mu factor saving of the state of the art. And in the HyperPlonk setting, k is like always larger than 13, and mu can be larger than like from 20 to 30. Therefore, it is almost like several hundreds of factors of saving to the state of the art. We also note that the protocol is efficient, meaning that communication and verification time are all logarithmic with really nice constant. So let's see how it works. So recall that our goal is to prove that fi zi equals yi for every like I from 1 to k, where zi is the evaluation point, fi is the polynomial, and yi is the expected claimed evaluations. And to illustrate the key idea, I just consider the the simplest case where there's only one evaluation point, which actually makes the batch evaluation not that making sense, but I just want to use this toy case to explain the high level ideas. Okay, so to prove that this fi equals fy equals yi, a key trick here is to rewrite the evaluation of fi in its interpolation form. And in the multilinear setting, this is the interpolation form is called multilinear extensions. So what we do is that we list the evaluations of this polynomial fi on the Boolean hypercube, and then actually the f's this evaluation exactly uniquely represents this polynomial, and the f's evaluation on an arbitrary point zi can be expressed as a linear combination of a tensor product. Then this tensor product is related to this point zi, and the coefficients are related to those evaluations on the Boolean hypercube. And basically, it's just the sum of them, which is basically essentially a sum check of the Boolean hypercube, right? And as we see before, the classic sum check protocol has a really nice property that the verifier only needs to query this multilinear polynomial at a single random point. Therefore, we successfully transform the batching protocol into a single evaluation. But of course, this is not very helpful here because we already in the beginning, we only have one single evaluation. So the question is that what we do if there are many evaluations? What if k is larger than 1? And a key property of sum check is that it's definitely batchable, right? It's like a very nice property that you can merge many sum check into a single sum check, and then in this setting you can still reduce the protocol into a single sum check, which only involves one single random evaluation. So the idea is now you can reduce the evaluations of f1 z1, f2 z2 to fk zk to a single random evaluation of some polynomial f star, where f star is basically a linear combination of the original polynomials fi. And you think about this, like the verifier, he will get the commitments to fi. So as long as the PCS, the polynomial commitment scheme, satisfies certain homomorphic property, the verifier can reconstruct this commitment to f star given the commitment to the fi. And then after that, it can check the corresponding evaluation proof for this f star R2. Okay, so that gives us a really good idea to transform many evaluations into a single evaluations. Okay, so I also want to note that these kind of techniques can have a really cool application in somewhere else, like for example, the commit and proof snarks, or more generally, enables you to efficiently prove the relations between the vector commitments. I won't talk too much in details. I just want to say that in this setting, we obtain an even more efficient scheme with proven time complexity only 2 to the mu. And this kind of techniques is very, very useful for us to building some commit and proof snarks from multilinear polynomials. And it's also one of the key building blocks of our Orion plus PCS construction. Okay. So after that, I want to focus on another cool feature that we achieve, namely extending HyperPlonk to also support lookup gates. So before diving into the technical details, I want to also mention really quickly why we need lookup gates. I think most of the audience should be convinced that yeah, lookup is useful, but let me just quickly go through it. So there are two very typical applications of using lookup. One is the range check. Sometimes given the arithmetic circuits, we want to show that certain values is in certain ranges, for example, from 0 to 16, right? And this is a so-called range check problem. And sometimes else, we also need to apply some bit operations over this on top of the circuits. For example, if you want to prove the correctness of a SHA-256 hash, it involves some XOR operation, for example, right? And the one bad thing is that if you only have addition gates or multiplication gates, it's very expensive to express this kind of functionality. For example, if you want to do range check, what you usually do is you decompose them to some binary values and check each binary values is exactly a boolean values, basically either 0 or 1. And this takes L gates, where L is the number of bits in this range. But if suppose we have some pre-computed table that stores these valid values, and if you can efficiently prove that a certain tuple or certain value is in the table, then things can become much more efficiently because one lookup gate suffices for us to implement both range checks or bit operations. So I think you are convinced that lookup is useful, and let's see how we can solve this problem in the multilinear setting. So given two vectors, f and t, well, t is some pre-processed table, and f is some online witness. How do you prove that each element in f is inside the table T? And the pool lookup is an elegant scheme that solves this problem. The idea is to interpolate this vector onto a set H, which is basically a multiplicative group generated by a root of unity. And now you can interpolate this vector into two polynomials. And then it transforms this lookup relation into another relation so-called multi-set equality relation over polynomials, which is much easier to be handled using ILP protocol. I will skip the exact transformation from lookup to multi-set equality, but I do want to highlight that the resulting protocol essentially uses the fact that you can very efficiently rotate the evaluation on polynomial by several positions. What you do is just multiply this so-called set H by a root of unity. So basically from f edge to f omega edge, you rotate the evaluations of on this set by one position. And this is very useful and is essentially used in the resulting pool lookup table, pool lookup scheme. And however, in our case, there's some changes. Now, first, the so-called interpolated set H is changed from multiplicative group into Boolean hypercube. And we change from univariate polynomial to multilinear polynomial. And in this setting, the existence of such a very, very simple and linear function of root of unity is no longer trivial. So we do need to find another types of generated function or next function that enables to rotate these sets. Okay. So to address this problem, our first step is to first view the Boolean hypercube as some field, which is binary extension field. And then we can replace this omega, which is a root of unity, with some other generated function for the corresponding multiplicative group inside this field. And we know that there's a really cool connection between this technique and some very old paper for building short PCP, which I found is kind of amazing. Okay, so let's see how it works. So let's consider a primitive polynomial p mu, which is of degree mu and with binary coefficients. And it's easy to see that this polynomial, the polynomial with binary coefficient modular p mu is isomorphic to the binary extension field f2 to the mu. And by definition of the primitive polynomial, X is exactly a generator of the underlying multiplicative group, which is basically f2 to the mu minus the 0 points. So now this gives a very good way to do rotation. Okay, so let's see an example of mu equals 4. So for every non-zero point in the Boolean hypercube, we can represent this vector as a polynomial with binary coefficient, right? Well, the vector are mapped to the coefficient of this polynomial. And then what we do is that we just multiply by this generator polynomial x, and we'll obtain some new polynomial with binary coefficients. And this translates back to a new point on the Boolean hypercube. And this gives us a really good map from u to its next function, next mu, and which looks like this. So this is, and I want to highlight that given that x is a generator, this next function exactly enables us to traverse the entire Boolean hypercube except the 0 points. And when mu equals 4, you can see the cycle looks like this. And this basically gives our way to rotate this set, right? So basically, when we want to rotate the evaluation of fx, what we do is just to compose this fx with this polynomial map next x. So f next x exactly works similarly as what we had before for f omega h. However, there are some caveats of this approach. This approach is that in this next polynomial map, the vector map, in some dimension, the function is quadratic. For example, you see here the b0 XOR b3. If you want to interpolate in its algebraic form, it should be the case that you have to interpolate as b0 plus b3 minus b0 times b3, which is quadratic. And because it has multiple dimensions, after you compose, the degree of the resulting polynomial will actually blow up. It will no longer become a multilinear polynomials. And that means in the underlying sum check protocol, it will be much more expensive. So given this issue, a key observation to solve this issue is that we found that actually we only care about the behavior or the values of this composed polynomial on the Boolean hypercube, but nothing else. So what about just simulate it using another multilinear polynomials, right? So recall that we have this next function. Recall the next function we have. And the key observation here is that for all the quadratic formula in some dimensions, these quadratic formula are all correlated to one single variable, b3, which is the last variable in this vector. And then gives us a really good way to linearize this function. So the idea is why not just enumerate the value of this last variable from 0 to 1, and then we can rewrite this next function and to make it linear, linearize these functions, right? So this gives our way to define a new multilinear polynomials as follows. Okay, so basically, if x3 equals 1, we'll trigger the left term. If x3 equals 0, we'll trigger the right term, which all maps to these next functions. And the key, there are two nice property about this f-shift multilinear polynomials. First is efficiently computable given only the oracle axis of f. So basically only involves, in order to evaluate f-shift, you only need 2 evaluations of the oracle f. That means in the underlying protocol, you don't need to send any extra oracles. You don't need to send the composed polynomial oracles. You even don't need to send the oracles for f-shift. You only need to send oracles for f, and it's sufficient for verify to simulate queries of f-shift using queries of f. And second is that its evaluation on Boolean hypercube is exactly consistent with this composed polynomial f next x. To make it more precisely, let's see some example, see the cases. For example, if case b3, if b3 equals 1, then we see that the left part is triggered, and the right part is inactivated and turned off, and the result exactly matches F next B, right? You can see here. And similar things hold true for B3 equals 0. If B3 is 0, the left term is inactivated and the right term is activated, and the result is still matches to F next view. So we can prove that the evaluation is exactly the same as F next X. So given this, instead of doing sum check or like multilinear protocols on top of F and F next X, what we can do is we can directly work on polynomials F and F shift, which are all both multilinear. And then this gives us really efficient and linear time lookup poly-IOP, and like which is really efficient and I think it's really practical. Okay, so finally,
just a question on the efficiency of that. So if you apply that next function, the F rotate function, more than once, then does that mean you get an exponential number of terms in the number of rotations?
That's a good question. Yeah, if you do if you want to rotate by multiple position, which is some case in the Halo 2, right? Like then we need exponential number of evaluations for F. For example, if you want to rotate by 4, you need like 2 to the 4 evaluation for F. So it's still an open problem how we can implement the shift by a long distance with very efficient protocol. And currently, because in the lookup case, we only need to rotate by 1 position, it's very efficient. You only need 2 evaluation of F. Yes. Yeah, very good question. Yeah. Okay, so finally, let me briefly mention our gram sort evaluation results. I want to say that the current implementation is only a proof of concept and also needs some optimizations. We also haven't fully implemented the lookup solution yet, but we are planning to implement all of them very soon and post a new benchmark in the paper. But even with the current raw implementation, I think HyperPlonk still did quite well. So the proof size is logarithmic, so it's worse than Plonk, but it's still comparable. And I think it's also really practical, and it's also much better than most of the multilinear-based snarks. It's only 6 kilobytes for a typical application, like for mu equals 20. Also, we compare our proof of concept implementation with a highly optimized Plonk implementation called Jellyfish. And it turns out HyperPlonk already outperforms Plonk at 2 to the 14 gates. And at 2 to the 20, it is already once faster than Plonk. And this gap will keeps growing because of the difference from coslinear time to linear time. And also want to mention that our scheme is also more parallelizable. So if we use GPU or FPGA or some hardwares, this gap can be even more significant. Also, we compare HyperPlonk with a variant of Spartan that's plugged with the KZG PCS for a fair comparison. And it turns out the Spartan is also very fast. But the key point here is that the difference here is that Spartan only works for R1CS, and it involves more constraints for certain applications like zk rollup or zcache or zk EVM. So HyperPlonk is still more efficient because it can represent this computation using much more succinct circuits. So the scale you need to prove is smaller. So the final prover time is still better in these applications. Okay, so I still want to say that, yeah, there are still plenty of space for our implementation optimization. And in particular, we see that the bottleneck of our HyperPlonk implementation is about the commitment part, the PCS part. So the commitment to the PCS and the evaluation opening of the PCS is account for most of the time for prover. So currently we are implementing we do 3 separate PCS batch evaluations, which is actually not a ideal way to do it because it's very expensive and there's no reason to do it if you want better efficiency. The reason we do it is just for simplicity of implementation, but we will try to combine them and just run a single evaluation proof, which we think that can expect significant improvements over the performance of over the implementation. And we will implement this very soon, and hopefully we can get a new benchmark, which also improves the performance of HyperPlonk. Yeah. And yeah, that's basically the it. And let me quickly summary what we have done. So first, we built a new Plonk-based multivariate poly-LP with a linear time prover. There's no FFTs, and there's much better hybrid gate, custom gate support. And we can also make the zero knowledge in the multilinear setting, which is actually not that trivial compared to the univariate setting. And also we extended to support lookup, and we built some new multilinear polynomial commitment schemes that improve the state of the art, which includes Orion plus that preserve linear time and have really small proof size, and a new FRI-based multilinear commitment scheme that's generically transform any univariate PCS into a multilinear PCS. Okay, so that's it. And thank you so much. Yeah, any questions?
Wow, Binyi, thank you very much for that presentation. Very comprehensive, easy to follow, and really interesting. So thank you very much for sharing. There were some questions going on in the chat. I chose not to interrupt you because Benedikt was covering them. Thank you, Benedikt.
Yeah, thank you, Benedikt.
Does anybody have any questions for Binyi or about this work in general? Binyi or Benedikt, or just about this work?
I guess I want to say, just for the questions in the chat, there were some questions regarding the precise cost depending on the gates and so on. And it's to be honest, it's a little bit of a complicated form, like it's a little bit complicated because basically, for example, high degree gates cost like less if it's a single variable, like raised to a higher power, right? That's one type of high degree gate. Another type of high degree gate is you have many wires or columns in the Halo 2 sort of language, and you say like you multiply all of them together, and that's more expensive a little bit. But you know yeah. So I think I answered a couple of questions regarding that in the chat. I don't want to go through all of them, but yeah, it basically depends on the specifics of the gate of what exactly the cost is.
I see.
Can you repaste that conversation in the chat? Because when you join late on Zoom, it doesn't show you the previous chat.
Yeah, I can find it. I can also find it. Does anybody else have questions about this work?
Yeah, can I follow up with a question on that? Yeah, thanks for the explanation. I think I understand how like the complexity of these gates works. But so if you have multiple custom gates, like the way that you merge them, does that not really blow up this this degree or like the complexity of doing the evaluation in the sum check?
Yeah, good question. So like we assume that the number of terms in this is constant, but of course you have like keep adding different complex gates. It definitely has some complexity on the evaluation checks. So you like we assume that you won't have too many types of complex gates at like connected by them, right? If so, for example, you have 1,000 types of gates, definitely it will affect the complexity of the sum check. Yeah. So our assumption is that this is constant, like less than 10 or something, which won't affect much of the overall complexity of the sum check. Yeah.
I mean, I think the way to think about it is that you need to like if you think of the gate as, you know, there's the gate formula, then you had like some nice yeah, at some point you have the gate formula, right? Okay. Essentially, like the prover needs to symbolically evaluate this gate formula. So that of course depends on, you know, how many terms there are. It depends on what degrees there are, right? Like if it's a high degree, right? Like where does this log squared factor come in? Well, you know, if it's a very high degree gate where I multiply many things, then actually, you know, like it's the multiplication of polynomials that then come in. But yeah, basically I need to symbolically evaluate this formula, like expand it once per gate. Is the way that I would formulate it. And it's not really simple to put that into one formula of what it is, like of what it could be, but we can bound the cost of it.
So this might just be more of a curiosity, but are there basically like pathological types of gates you could construct where you can't do this like sort of polynomial, symbolic polynomial multiplication trick, and you're stuck with sort of the naive d squared evaluation time? Or
I mean, so the d squared evaluation time is essentially, it's a symbolic evaluation. I just do it in like, right? I just do it in evaluation form. Right. But, you know, I mean, I think that the d-log squared d algorithm that we use actually does rely on FFTs. It just relies on small FFTs. So, for example, if you're in a non-FFT friendly field, then you maybe wouldn't use FFTs. You would use something like Karatsuba's algorithm. But no, I didn't. Binyi, like maybe.
And
you
also
can
usually,
this, but I don't know. Yeah.
Also, usually D is not that large, right? It can be large, but it won't be large as 1,000 or 1 million. It's only like 100, and usually like I guess using Karatsuba is already sufficient because like it's already D times square root D, which is only a very small factor compared to that. So yeah, I think if you want to have a like using non-FT friendly field in the practice, you can definitely use Karatsuba and it won't affect much of the efficiency.
Thanks.
So I have a couple of questions. So to follow up on that, is this technique also applicable to like standard Plonk? You know, so this for this higher degree custom gates, is effectively you're composing, you know, two protocols, right? Like you have, you know, first opening up the multilinear, and then you have, you know, opening up this like custom gate committed polynomial, right? Can we just do this for standard Plonk as well?
You mean by standard Plonk constraint system or standard Plonk proof system?
Yeah.
So for proof system.
So instead of the verifier doing this polynomial locally, the prover will effectively compose two different openings, right?
Yes. You are saying, so what's the main question? Main question is like this kind of high degree custom gate technique can also be used in the univariate setting. Is that your question?
Yeah, that's the question.
The key reason is that it's not that efficient. It's exactly as mentioned before, that in the univariate setting, you don't have sum check, but what you have is quotient check. And if you do this kind of techniques, like finally you have to commit to a really large degree quotient polynomial, which is definitely less efficient. So it limits the practicality of this approach in the univariate setting.
I see.
That's the answer question.
Right. This is exactly what Binyi wrote there, and that's the important part, right? Like in univariate sum check, we commit to one quotient polynomial, which is of degree d times n. In this sum check, in the multivariate sum check, I also commit to like some sort of polynomial in every round, but that one is only degree d, not d times n, and there's log n round. So essentially it's d times log n group operations versus d times n group operations. So that's why like having super high degree gates in univariate Plonk just doesn't make sense, because whatever factor you save, you will totally lose again when you have to commit to the quotient polynomial.
Yeah, in summary, definitely can use high degree gates in univariate setting. You can give the really succinct circuits for certain applications. But the point is the trade-off is like it also makes the proving speed per gate also much worse in this univariate setting. So it won't make sense for you to do a really high degree gate for univariate setting.
Yeah, in particular in the univariate setting. So it's particularly inefficient to, if you have just one gate that has a very high degree, then you're paying that cost for everything.
Yeah.
So you want the degrees of your gates to be roughly the same, and that's also part of what limits it.
Right.
Yeah, I just misunderstood. I think I didn't think through the quotient polynomial part. So my second question is, what is, if you want to like estimate like the recursion threshold for this, because there's like for some check you have this log factor. I'm just thinking of, from a practitioner perspective, would this be useful as an inner proof, right? Because then it's crucial to look at like how efficient is the verifying circuit. So, but do you think there are estimates on that?
I think in terms of verifier complexity, like verifier circuit complexity is still only one PCS evaluation proof verification. But of course, the multilinear PCS verification is more expensive than the univariate setting, right? In the univariate setting, it's just a constant number of pairings and a small MSM. But in the multilinear setting, it's log n of them. But I think concretely, it might give some overhead. I haven't count this. I haven't like exactly compute this, but I don't think it would be super high. It can be efficient, but maybe not that efficient as a univariate verifier, but it still be efficient. And I think because of the proving time itself is already fast, it might also make sense to do some recursion in some setting. Yeah. But good question. I haven't like very carefully calculated the circuit complexity for verifier yet. Yeah. Thanks.
Yeah. So the cost breakdown on that slide, that was just for the prover, right? Do you have a similar cost breakdown for the verifier?
I mean, I think the verifier essentially needs to evaluate the gate formula once, at least, right?
Yeah. Okay, cannot.
Yeah, no, I mean, I think that's exactly it. The verifier just evaluates the gate formula once. That's
okay.
And well, no, actually, no. The other thing is that the degree of the sum check increases, right? So in standard sum check, you actually send over the entire polynomial. But one thing that we do is you just send over. Like if you have a high degree gate, you may as well just send over a commitment to a univariate polynomial in every round of the sum check. So there's no additional cost to the verifier.
Yeah, so basically the verifier cost is basically two PCS check. One is the multilinear PCS check and one batch univariate PCS check. Well, because in the sum check of high degree gates, what we do is we just send univariate oracles in each round. And there are some univariate oracle queries, but we can definitely use a halo infinite to batch all of the evaluations. And then finally, just one univariate PCS check. Yeah.
I see.
Would it be fair to say that there's basically additional log factor in the verifier cost? I mean, assuming that like opening.
Yeah, we can think about that. Yeah,
okay.
So there's a question in the chat, Aurelian. I hope I'm saying your name right. If you want to ask it out loud, feel free, or it's up to you.
Yeah, I can. Actually, if you could go like way back to the first slide that explains the hypercube encoding. And what I'm trying to understand is what's the cost of adding like one more variable or one more wire, and what's the advantage of the hypercube compared to like other ways to identify wires?
You mean
in the encoding part, right? Like I think way in the beginning.
Yes, yeah, like first slide almost.
It's really quickly change. Let me just.
And I'm trying to understand how the hypercube part comes in, because you can do a more compact encoding, right, with like two variables that are indices into like a 2D grid, and you can also do a less compact encoding, like one hot, right? So where is the hypercube important?
I mean, I think it's just the trade-off, right? I think that the number of rounds of the sum check decreases if you're using a higher degree cube, or I guess like, yeah, if you're using say like base 3 or whatever, but it only decreases by a factor of log 2, like say it's h, right? Then number of rounds of sum check decrease by a factor, I'm gonna write it down, by factor log 2 of size of h, right? If we're encoding over h to the whatever. But the degree of the sum check, so the degree in each round increases by a factor of h. So
yes.
I don't think it's a worthwhile trade-off. But
what is h? What size of h?
H is like say, yeah,
Boolean hypercube size, or yeah. So the number of gates.
H equals
The number of variables basically in the multivariate.
Log h is the number of variables, right?
No. I think it's the base, right? Like it's like 0, 1 if we're using a Boolean hypercube. I thought your question was, what if we don't use 0, 1 to encode, but what if we use 0, 1, 2?
Yeah.
Oh, I see. That question, I see.
So,
yeah.
So I think it's basically, so if we call that thing h, then you can make it bigger to decrease the rounds of the sum check by a factor of log 2h, but it increases the complexity of the degree of the sum check by a factor of h. So yeah, it usually doesn't seem like a worthwhile trade-off.
Yeah, I would.
If you go to the extreme case,
I was actually doing some.
Yeah, I got it. Thanks.
Yeah, I was actually doing some back of the envelope calculations about this, and it seemed to me that that an arity 4, so your base is 4, might be more efficient because that you still have a relatively small number of additions. If you look at the generalized sum check that works with an arbitrary base, each round is still not particularly complex in that case. So then it may actually be more efficient to use it slightly.
Actually, I think we tried this method before.
Oh, okay.
Yeah, and the main reason why it's not more efficient is because of like high degree gates. Like I remember that when we use like encode to 4, like for example, you definitely decrease the number of rounds. Like you decrease the number of rounds for sum check. But actually, if you have high degree gates, I forgot the exact computation I had. But if you have like a high degree gates, then each round the complexity is much larger. It's not like it's not from n to half of n to fourth of n to something like that. It's like there's some quadratic blow up. And actually, if you have like larger base, like from 0 to 4 or something, actually the complexity for high degree gate is actually worse. So that's why we stick with binary hypercube. Yeah. But in the just the linear setting, the multilinear setting, there's no difference, I think. Or maybe there's some efficiency, as you said, like there in terms of multiplication versus addition, there might be some trade-off, and might be having higher degree might works. But to me, I think seems like the same. But in terms of the high degree gates, definitely I think the best approach is to using Boolean hypercube. Yeah.
Well, I mean, at least in terms of the scale, the group operations, say you go to the extreme of only 2 rounds. So you take a cube of square root n on square root n. So definitely the group operations will improve, right? Because you have n plus d times log s. So now log s is like 1. And I wonder if there's a chance that you got a decreased efficiency because, you know, since you're thinking of the degrees as constant of the univariate, you're using like something for polynomial interpolation that's, you know, for very small domains. But my guess would be that, I mean, the proof size would be huge, but in terms of proof over time, actually, my guess would be that if you use FFT for the univariates that come up, then the extreme of like just two variable might actually work well.
So actually, I think for group operation, it's actually not a big change, because you see that it's n plus d log s, right? Like constant times n plus d log s. And in practice, n is much larger than d, right? Even you change from log s from log n from 20 to 2, then d log s is still a very negligible part compared to the total number of.
I think maybe what I forgot, what I'm suggesting, there would be an additional square root n, sort of like the univariate you'll send will be, it will be like of degree, maybe square root n times times d. So I guess, right, the general formula, it's d times the individual degree of the witnesses, which in your case is just 1 times log s. So so in what I said, I increased that 1 to like square root n. So I forgot about that.
I mean, there should be, right, like, it is true that there should be a family, right? Like, essentially, if you formulate things correctly, then if you only have one round, you should get back to normal univariate Plonk.
Maybe there's a trade-off, like intermediate point, that
it's a trade-off also. Like you save on the var cost, because imagine on one side of the extreme you have univariate, and on the other side you have HyperPlonk, right? Hypercube. And I think really, like, are there basically trade-offs in between where you trade off prover, like larger prover time because you have higher degree, univariates, FFTs, but you have like, more like less variables, right? So therefore you have like less complexity on the var side.
Right. So you mean with less number of rounds, maybe you can get better verified time. But I think whether is in that case, is it sufficient to have a multilinear PCS? Do we need to have some multivariate PCS maybe, right? Because
I think it's probably multivariate PCS. So like you want to pack the entire like constraint, in a multivariate, so. Like on one side, like a univariate, it's just like a line, and on the other side you have hypercube, but now it's like basically a hypercube of higher dimension. Like we're not a cube anymore, right? We're each dimension. You pack more elements, maybe.
I see. Yeah, good question. I need to check. I think but it is it's a good thought. Yeah.
I mean, what is interesting is that even with, right, like the reason why, one of the key reasons why univariate Plonk is bad for high degree gates is because of this quotient polynomial, right? That is of degree n. It could be that even with actually with 2 rounds, I don't know if that's true. Well, that even with, like, say you extend it to a few rounds, right? Like if you think of Plonk being 1 round, HyperPlonk being the other extreme, like log n rounds or mu rounds. It could be that even with a few rounds, the degree of the quotient polynomial also always like decreases exponentially. So perhaps, like even a few rounds are enough to make it a non-factor. That's certainly possible.
Yeah, this was why my intuition was that using a relatively small base, but not 2, so say 4, the degree of if it sort of scales smoothly between univariate Plonk and HyperPlonk, then I wouldn't expect the cost of the high degree custom gates to be that much greater. So I'm surprised if it is. But you've done the experiments, so.
Yeah, I just think that in the end, like, I mean, we mainly cared about prover time. I think the prover time is going to be optimal for HyperPlonk. Could be if, like, you really care about verified time, that there's some other spot that's in the middle that's better, but I don't know. I always feel like,
yeah,
I feel like we're maybe at a point where you should just care about prover time and then use recursion to bring down the verified time. Like, I don't know.
Yeah, exactly.
I mean,
it's in the recursion case, but you care about the verifier a lot, right? Because the verifier is then it's verifier secret, and then it has a prover. So that's a total.
But I can always use recursion to bring the verifier down.
Well, even with recursion, you still care about verifier time because your recursion threshold is going to be I don't know 2 to the 12 row circuit, or maybe 2 to the 11 if you're particularly clever about it. And so it's still a few milliseconds. So it depends what you consider an expensive verifier, really.
Yeah.
Yeah, I mean, I guess like it's like, I feel like expensive verifier is defined by what we happen to have as EVM precompiles, which seems a little bit like arbitrary. Like, you know, so, maybe we should just.
How does the recursion work? Like, how do you verify it as a secret?
So you just see this verifier as a circuit, right? Like the circuit is NP complete, you can definitely model every computation. You just beyond prove this circuit verification, or beyond proving the circuit correctness, you also prove that verifier will accept this proof. So that's the idea of recursion. And finally, yeah.
Yes. So I mean, you can use like Halo. You want a cycle of 2 curves, right?
But you can use 2Chen, for example, if you're okay with that. Like there's
there's also much more. Yeah, I mean, there's, you know, for the specific case of KZG polynomial commitment scheme, right? You can use something like IPP in a pairing product to reduce all of the pairings into one, right? Like there's much, like there's things that we can do that we already know pretty well. Like if the verified cost is actually a concern.
It seems like all of the techniques for optimizing recursion are independent of the difference between Plonk and HyperPlonk, as far as I can see.
Yeah, I mean, it's just that in HyperPlonk you have multiple pairings, right? Like if you use it with KZG, you have your pairings, and we have techniques for combining all of those that are very, very efficient.
Yeah. Still, I also want to say that the SNUC verifier is more related to the PCS part. Like you should think about HyperPlonk as poly-IOP, right? Like you can plug it into any PCS, right? Like one particular instantiation is KZG, and maybe you can do others, or even our new multilinear commitment scheme, like proposed in the paper. So with different PCS, you have different PCS verifier circuits. Yeah.
I mean, if you're using accumulation like in BCMS 20, then the accumulation verifier does not need to do a pairing, even if you're using KZG. So that I think that's the PCDL scheme in that.
Right.
Delegated to the outer verifier.
Exactly.
Yes. So
but, did you say that most of your work was in the field, like field operations, in the sum check?
Mm-hmm.
Or was it about the verifier?
So for verifier, I think like using our like univariate oracle, like the classic sum check also has some field operations, right? You need to evaluate like the round polynomials at some points 0, 1. But in our setting, the high degree setting, what we do is to send univariate oracles, like which is basically univariate commitments. And then finally, you need to the verifier's cost is just to check the evaluations of them, and basically just a batch PCS evaluation for univariate polynomials. So basically, there's no cost about sum check related to the degree of the D and of the field, like not much field operation. So as I said before, basically the bottleneck of verifier is just one PCS evaluation check for multilinear polynomial and one batch PCS evaluation for univariate oracle. Yeah, for univariate polynomial. Yeah, that's basically the verifier.
Yeah, that makes sense. Yeah, because the origin of the question is that when you use trying to do recursion on a curve like BN 254 that doesn't have a cycle, right? And the verifier is then it has to do group operation in a non-native field, right? Like in this kind of field, and it's doing elliptic curve operation in the base field of the inner circuit, right? So the group operations are extremely expensive, and the field operations, well, it's the same field, so they are very cheap.
So I think it comes to the previous question. So basically, if you want to stick with KGG, then yes, you either use you can use 2-chain, right? You can use 2-chain with BW curve versus the BOS curve, and then you don't need to do any non-native operations like this native group operations. So the circuit will be still efficient. So.
Yeah, so that's actually opposite whether you have a cycle or not. Then the cost of group of field operations are reversed, so it depends which one you can use.
But yeah, as I said, in this setting, you don't need to use cycle. You just use a 2-chain. That's enough. Yeah. But of course, if you want to do like more layer of recursion, then yeah, maybe you need to cycle or use some like halo method, like accumulation.
Oh, I see. You mean not a cycle, just a chain.
Yeah.
So just to clarify, you're saying most of the operations that the verifier needs are in the same field, but what proportion are in the different field? Because obviously some must be in a different field. Go on.
I think it's just that the verifier mainly does group operations and pairings, I guess.
Oh, I see.
Okay. Or it mainly does KZG. It does essentially polynomial commitment verification. Like that's really okay. The verifier does, as Binyi was saying, one, it has 3 things. It evaluates the gate formula once at some point. It has to check all the challenges. So I guess 4 things. And then it has to open one multilinear PCS and batch open mu univariate PCSs.
Okay, I'm just trying to visualize which fields these operations are in. So say you're using a cycle like
the same. What do you mean?
If you're using cycle, like you're saying doing recursion, or without recursion. Without recursion there's no cycle.
With recursion.
With recursion. So if it's 2-chain, then I think, oh gosh, with recursion, then I think all our BW curve, like field operation is BOS, right? And a group operation is BW, right?
Sorry, I didn't hear what you said.
Oh, sorry. So if you do recursion or do 2-chain recursion, like then all the group operation are related to BW curve, and the field operation are the BOS field of BW field. Yeah.
I would say the non-native group operations that you need to do is evaluate the gate formula once. That's the non-native group operations that you need to do. The rest,
okay,
you can,
so same as in Halo 2.
Yeah,
you can use the accumulation, whatever your favorite accumulation scheme is, right? We now have a bunch of them for the PCS openings. And then you would use the non-native field operation. The additional non-native field operations are the evaluating the gate formula ones.
Makes sense.
So guys, I just quickly wanted to say we're at the end of the allotted time, but if there's still questions, I'm happy to keep it going. And if anyone needs to sign off, I think a couple people have already jumped off, but yeah, feel free to jump off. If there's any more questions, we can keep rolling. If Binyi and Benedikt, you guys have time, because I want to be respectful of your time as well, or we can conclude it here. So I'll pause for a second, see if anyone has any other questions.
Yeah, I'm fine. I still have the room. 0 minutes. Yeah.
Okay, cool. Thank you, Binyi. Does anyone have any final questions for Binyi and Benedikt? By the way, thank you guys so much for answering all the questions comprehensively to this point.
I have a question. So the paper talks about like how to build a state machine with some repeated transition function. Have you, and one of the ways to do that is to use your like polynomial shifting technique so as to not like duplicate the inputs or the outputs of one step to the inputs of the other. Do you know of a way to do like periodic, you know, the equivalent of periodic columns with this polynomial shifting technique? By that, I mean like that you would pre-process some smaller polynomial of constants and then be able to sort of have the verifier repeat it through the entire trace of all of your, you know, however many times you want to repeat that, if you've seen that technique.
So the question is whether we can do something similar to air, right? You can do like some constraint period of time, like apply some constraint like every 10 step or something like that.
Yeah, exactly.
Right? So one thing you can do that's using a selector, right? You can always do a selector, have a selector say this is 0 for every like 10 step, and the 11th step you pick it, move it to 1 or something, right? As you said, you can do some preprocessing. That's one way to do that. And another way is to do shift, but as Dara just asked, like the shifting by more like longer distance is more complicated. It's more expensive using our approach, like in terms of, because the number evaluation will be like exponentially increased. So this is still open question whether we can do really efficient shift by a large instance. Yeah.
Yeah, I was trying to figure out whether there was any different representation that would still give you a permutation on the hypercube excluding 0. And I think so. Normal basis doesn't work because that doesn't give you a full permutation with an efficient shift. But I don't know whether there's anything else that might work.
Yeah, so in summary, it's always doable. You just do have some preprocessing, like have a selector or have a permutation, like Oracle, like which are preprocessed. Or if you want to do online without any extra overhead, as we did for lookup, then you need to think more. Like if you just shift by 1 or 2, definitely is doable and it's efficient. But if you want to do a like longer period, then yeah, then there's also an open question in the multilinear setting. Yeah.
Yeah, if you could do something like a power of 2 shift, then obviously you can build any shift from that.
Yeah.
But I couldn't see any way to efficiently do that.
Yeah.
Okay, thanks.
Thank you.
Okay, going once, going twice. Any other questions for Binyi and Benedikt? All right, going 3 times. Sold. Awesome. Okay, hey guys, thank you all very much thank you very much for joining today. Binyi and Benedikt, thank you both for being here. This is a really great session, and we'll post this on YouTube here soon. Binyi, if you want to share the slides with me, you guys don't have to. If you'd like to, I can put them up on SlideShare, and I'll put it on. I'll link it in the video description. All right. Thanks, guys.
Okay. Thank you.